Hi, I welcome you all. Today's presentation involves introduction to thin cylinder, the hoop stress and the longitudinal stresses, followed by the change in dimensions, that is the length, diameter and the volume. And it will be followed by a sample problem and review questions in conclusions. The main objective of today's presentation is to understand the thin-walled pressure vessels and the principal stresses that is acting on the walls of thin cylinder under the internal pressure. What is a pressure vessel? A pressure vessel is a container designed to hold gases or liquids at high pressure. How a pressure vessel is fabricated? A cylindrical pressure vessel is fabricated by rolling of steel plates. So once it is fabricated, extensive testing is carried out by hydrostatic pressure testing for leak proofness. Some of the important design parameters while manufacturing a pressure vessel are the maximum operating pressure and temperature. So what is the most common shape of a pressure vessel? Theoretically, we can make pressure vessel using any shape, but in engineering practices, we are mainly considered only on cylindrical as well as spherical pressure vessels. So what is a thin-walled pressure vessel? So if you consider the ratio of inside diameter to that of the wall thickness, and if it is greater than 20, then we can call this as a thin-walled pressure vessel. And if a pressure vessel is pressurized from inside, we can see there are three major stresses that will act on the walls of the cylinder. And the first one is the hoop stress or the circumferential stress. The second one is the longitudinal stress along the longitudinal or the axial direction. And the third one is the radial stress. So in our analysis, if we comparing the values of hoop stress and the axial stress, the radial stress is very less. So hence we are considering only the hoop stress and the longitudinal stress. So in order to calculate the values of hoop stress and the longitudinal stress, we are making some assumptions. So first assumption is there is no change in the cross section of the wall and it is assumed to be uniform. Since there is no change in cross section, the stress distribution will not vary significantly and it is assumed that it is uniform or constant. So based on these assumptions, we will be able to calculate this hoop stress and the longitudinal stress. And some of the important terms that describe the calculation is shown in the table, and all the terms are described with units. Consider a thin-walled pressure vessel with inside diameter D and an inside pressure P. If you cut a cross section and across the longitudinal directions, we can see due to this internal pressure, it is trying to increase the diameter, right? So it is trying to increase the diameter. So if the system or if the pressure vessel has to be in equilibrium, we need to calculate what is the force acting on the wall of the cylinder. So due to the inside pressure, we will be able to calculate the force, that is P is force is that is pressure into area. So here the area is the projected area. So that we can calculate as the diameter into length. So if this inside pressure is resisted by the circumferential stress or the hoop stress. So if we equate these two equations, that is P into D into T, that is a pressure force due to the internal pressure, and the resistance offered by the walls of the cylinder, that is 2 into sigma theta into T into L. So by equating these two equations, we can see that the hoop stress or the circumferential stress is given by PD upon 2T. And you can see a figure here. There is a broken pipe, and this pipe is failure due to hoop stress. And this is a very much representation of your garden hose. And if you increase the pressure of the water, and there are potential chances the crack may be developed in the which direction? The crack may be in the longitudinal direction. The crack is developed, and this crack is due to what? Due to the hoop stress or the increase in the hoop stress. And this equation is very important in calculating the hoop stress, that is sigma is equal to PD divided by 2T. If you consider the same cylinder, and if you cut a cross section perpendicular to the longitudinal direction, we can see that the inside pressure is trying to enlarge the length of the cylinder. So if we arriving the force balance, that is force is nothing, pressure into area. So Pi is the inside pressure, and the area is given by pi d square by 4. And if we equate this area with the circumference of the cylinder, and this pressure force is resisted by the longitudinal stress, and that is given by sigma L into pi d into T. So if we equate these two equations, we will get sigma L is PD upon 4T. And if we examine carefully the hoop stress and the longitudinal stress, the value of longitudinal stress is half of that of a hoop stress. So this is the one of the major reason. If you want to store high pressure liquid or gas, we are going for a spherical pressure vessel. In a spherical pressure vessel, there is only one stress, that is the sigma L, that we can call as PD by 4T. So for a given vessel, this hoop stress is half compared to that of a cylindrical pressure vessel. So here I will quickly explain the effect of strain and the change in dimensions. So before discussing, I request you to recollect the generalized three-dimensional Hooke's law. Here, since the radial stress is, the value of radial stress is very less, we are not considering the radial stress. So we are by using the Hooke's law, we will be able to calculate the change in length, the change in diameter, or the change in volume. So first we will discuss on the change in length. So what is linear strain? The strain is, that is the change in length divided by the original length. So change in length is given by, that is the linear strain multiplied by the original length. The strain is nothing but stress by Young's modulus. So in the longitudinal direction we have sigma L, that is sigma L divided by E. And if you refer the three-dimensional Hooke's law, we have to write two more terms, that is minus mu into sigma H. since sigma r, the value of sigma r is very less, we are neglecting that term. So if you substitute the value of longitudinal stress and the hoop stress in this equation, we will be getting delta L, that is change in length due to the internal pressure, that is given by PD upon 4TE multiplied by 1 minus 2 nu into L. Here it is clearly shown that the diameter strain, that is equal to the hoop strain. So what is the change in diameter? That is diametral strain multiplied by the original diameter. The hoop strain, if you recall the three-dimensional Hooke's law, that is hoop strain is given by 1 by E multiplied by sigma theta, that is the hoop stress, minus nu into sigma L, that is the longitudinal stress, all multiplied by capital small d, that is the diameter of the vessel. And if you substitute the value of hoop stress and the longitudinal stress, we will be getting the change in diameter is PD square upon 4TE whole multiplied by 2 minus nu. The next one is change in volume. Change in volume is the volumetric strain multiplied by the original volume of the cylinder. And it can be seen that volumetric strain is equal to sum of strains in three mutually perpendicular directions, that is epsilon L, that is 1 in the longitudinal direction and 2 in the hoop direction, that is 2 into sigma epsilon H. So the volumetric strain, that is given by 1 by E multiplied by sigma L, that is the longitudinal strain, minus nu into sigma theta, plus 2 by E into sigma theta minus nu into sigma L. And if you substitute the values of sigma L and sigma H, you will be getting the volumetric strain delta V, that is given by PD upon 4TE multiplied by 5 minus 4 nu into V. Now we have derived three equations, that is one is the change in length, change in diameter and change in the volume, and we use these equations to solve one numerical problem. So we will try one example on a thin cylinder. So a thin cylinder of 60 millimeter diameter, 225 millimeter long, with a wall thickness of 2.7 mm, and it is subjected to an internal pressure of 6 megapascals. Assuming the Young's modulus E equal to 200 gigapascal and Poisson ratio is 0.3. So calculate the following. So first one, hoop stress. Second one is longitudinal stress. Third one is the change in length, and the fourth one, change in diameter. Normally these questions can be asked for 13 marks or 14 mark questions. And the first step in solving the problem, please write down the given data, and we have to be very careful with the unit also. So here I have shown everything in meters. So thin cylinder diameter, that is 60 millimeter, so that is 60 into 10 to the power minus 3 meter, and the length of the cylinder, that is 225 millimeter into 10 to the power minus 3 meter. The wall thickness, that is 2.7 mm, that is 2.7 mm into 10 to the power minus 3 meter. And the internal pressure, that is 6 megapascal. Megapascal is 6 into 10 to the power 6 Newton per meter square. And E is equal to 200 gigapascal, that is 200 into 10 to the power 9 Newton per meter square. So all the given data we have written. The next step is write the formulas correctly. So first one, the hoop stress. For the hoop stress, we know that sigma theta is given by PD or 2T. So if you substitute the value of P, D and T in this equation, we will be getting hoop stress, that is equal to 66.7 mega Newton per meter square. So similarly, we can calculate the longitudinal stress, that is sigma L, that is given by PD upon 4T. And we can see that the value of the longitudinal stress is half of that of hoop stress. So next one is the change in length. The change in length is given by the equation PD over 4TE into 1 minus 2 nu all multiplied by the length. So if you substitute all the values in this equation, we will get change in length, that is delta L, that is equal to 15 into 10 to the power minus 6 meter or 15 microns. So next one is the change in diameter, that is delta D. The equation for the change in diameter is given by PD square divided by 4TE whole multiplied by 2 minus nu. So if you substitute the values, we will get the answer, that is delta D is equal to 17 into 10 to the power minus 6 meter. So only thing in solving the problem, you should be very careful about the units and you have to write the formulas correctly. Thank you. Here I have given 3 review questions and I request you to kindly go through these questions and answers, and for more questions I request you to refer any strength of materials textbook. Now I am going to conclude this lecture. Hope this was helpful to understand about pressure vessels and the major stresses associated with the pressure vessels. I thank you for watching this video, and if you have any doubt, please do contact. Thanks for watching.